All right, so like I was saying, this is a kind of a continuation from section 31 and into section 32. Note that I'm not going to be able to talk about everything on here. So there's a lot more in the curriculum. In fact, there's a really good labs. I'm going to strongly suggest for you guys to make sure you go through those labs, private, play around with it. That will really help you hone in a lot of how this works, okay? Especially for 32, right? But kind of continuing from 31, just a quick review. We're kind of continuing on this notebook is we talked about trends for time series. So we talked about looking for stationary, stationary time series and saying like what those kind of look like, what things are not stationary. So for example, saying the mean is not a function of time, the variance, the covariance, and we can see kind of like these extreme, like kind of little cartoon models. I think the curriculum has some very similar images here. This is actually borrowed from, I borrowed these images from this blog, which I thought was a pretty good job of explaining a few things. Kind of going through, we kind of want this no trend here. You can see we have some other trends that we'll notice, like for example, linear trend, upward trend, downward trend. We'll sometimes see exponential trends. So this is where basically you can see, I think I noted this last time, is that exponential trends are particularly interesting because we can see at the very beginning of this exponential trend actually looks very linear, and then after a while it can actually kick up. So these are kind of an interesting one to kind of find. It's like when something becomes what looks like a linear trend actually ends up being an exponential. So this kind of a little thing to keep an eye on. We talked about periodic trends, which is probably something that you're kind of familiar with. So for example, the seasons change. We have the temperature change over year to year. So just kind of know like, okay, like this is another kind of trend we can look for, right? And here's another one. Here's one, I think, was your temperature degrees in Celsius over multiple years. So you can kind of see is that, this is over about 1 year. So you can see here, or 2 years, and you can see here that fluctuation, even though there's individual little changes, you can see that overall trend, this periodicity within here. And here's a little more explicit on a data set that we'll look at a little bit later. I think it's like passengers on a plane. But you can see here is the fluctuation back and forth. Okay. We talked about assessing trends. So for example, rolling statistics, we'll see this a lot. We're averaging over different data points. So for example, this is a window of like 6, is that we're essentially rolling over this window and moving this window across our time series and averaging out. And that's what this blue is, or not this blue, this red right here is moving up. It basically smooths out this graph. If you make it too small, basically you won't really get that smoothness. If you make it too large, you're gonna lose some interesting features of that time series too. But this can be helpful to see this overall. It's like, well, we know what this trend is going in this general exponential function. We can then find out the little extra parts. So we'll see this in how we can subtract off that rolling mean. And then we talked about the Dickey-Fuller test. So this is a test that we can use for statistical, it's kind of like a hypothesis test for saying if this time series is stationary. And so this is actually built into stat tools in Python. So this is something, or stats models, and can be really useful. Well, we'll use this a lot to assess if your model or your time series is in fact stationary. Okay. All right, so that kind of leaves us to where we are now. Any kind of quick review questions? I know, for example, Adam, you weren't here last time, but hopefully you're able to keep up with some of the stuff. Cool. All right, so I started talking about last time, I think, about removing trends. And so this is when we say, okay, we see our time series has trends, it's not stationary, it's non-stationary. We want to kind of remove the get to a stationary series. And this allows us to basically see things, seasonality or different trends, stuff like this. So kind of checking with you guys, why do we want to get a stationary series? What are some reasons we might want that? Any guesses?
The data would be more normal.
Okay, good. So like, yeah, you might have it more distributed normally. So you can actually, this kind of leads into, I almost like make this kind of like internal comparison of like how we want our data to be normal when we do a lot of statistical tests. It's the same way that we do statistical tests, we use this for a stationary series. So it's a good kind of comparison, like in my mind at least. So yeah, good. So yeah, again, we really want to get rid of that time dependence out of there. Like we kind of want to be able to say, okay, if we get get rid of that dependence. If we can get rid of it, we can explain it essentially. We get like all this, I call it like the noise. And it's not really noise. It's basically the noise is other stuff we can explain with other features and such. And again, noise might not be the right word in this case, but that's kind of in my mind. It's like you're getting rid of this stuff that you can't explain, and then you're left with stuff that like, oh, I don't know how to explain this art. And that's good because now we can say, okay, let's dig deeper and actually try to see what this is. Or maybe it's other randomness that we don't have features on to be able to explain this part. But at least then we get to the parts that we did know how to explain.
A real world example of this is if a company is looking at its profit margins. Specifically, academic institutions have an almost predictable decrease in revenue around like May, June, and July. And so once you have detrended, you can, if you take out the overarching trend, you can look at just what's going on month by month and see how autocorrelated it is. Versus if you want to not panic and think the sky is falling every time you have a temporary dip in revenue, you might want to take out the temporal nature of it. So it's more like, are you focusing on your 50-meter target or your 300-meter target?
Thank you, Aubrey. Yeah. And so this is like, again, you're trying to find if you can explain parts of it. So this is kind of like why we get to the stationary, like Aubrey said. And then again, Aubrey has more experience, to be quite honest, than I have in time series. So thank you for contributing that. All right. So yeah, so that was kind of a quick, like, why are we trying to get it to be stationary? Right. Cool. So let's leave it to the next part. So there's some ways we can do this. One is a log transformation. This is a pretty common thing that we'll do. So this is most of this stuff actually comes from the curriculum. So just know that you'll see similarities if you go through the curriculum on this section. So here I have actually the time series before it was transformed at all. And then I actually did a log transformation on that time series and a square root transformation just to kind of do this comparison. So you can see here, this is the original right here. And you can see it's getting into the exponential part. And when we do a log transformation, you can actually see it gets into a more linear, which hopefully that makes sense, is that we're kind of undoing the exponential. And so we're essentially kind of flattening this out and we're punishing really large values essentially. That's essentially what we're doing with a log transformation. One thing that we might notice on this though, is that we're producing this heteroscedasticity. And you can see here is that our variance is changing over time. And that's not ideal, you know, but like this might be something that might be worth us doing to be able to get to this point so we can actually do something with our trend. Here's another one, is the square root. And the square root basically is similar in the way of like how the log transformation is doing stuff. It's also punishing large values. It's doing it in a slightly different way. So you won't get as much heteroscedastic, but maybe in this case, it looks closer to linear. I still think there's a little bit of a bonus, but it's a little hard to tell, but you still get that heteroscedastic over here. And it's debatable, maybe. I'm sorry, yeah.
So for this, you're not applying like the log transform on the dates, right? The dates are staying the same. You're applying the log transform on the, like, in this case, the monthly sales.
That's right, yeah. Okay. So you're only applying it to essentially that target, that y-axis here.
Got it, okay.
It wouldn't make sense to do a log transformation on that date. Cool.
Just making sure.
Yeah, no, that's good. Good call, good check.
Right. I have something to add here if you don't mind. So what if a log transformation and square root are not actually solving your problem, or you're getting it slightly more linear, but the heteroscedasticity is bringing about some grumbles and gripes? There is a glorious process called Box-Cox Transformation, and will actually detect, for example, in this case, an exponential distribution. It tells you what the lambda is in the exponential distribution, and it tells you the degree to which you need to transform your data so that it normalizes it. As I'm sure we all know that log transformation and square root aren't one size fit all. Sometimes you're gonna have negative exponents, sometimes you're gonna have positive ones or fractionals, and you don't know until you try a bunch of them.
Definitely. Thank you, Aubrey. No, I didn't know about that, so that's something be cool.
Yeah, log transformations are usually used for percentile differences and also for prices. So if you're using time series to adjust price elasticity, you're going to use a log transformation, yes, every time. But a lot of other situations, log transforms, when used appropriately, will decrease heteroscedasticity rather than increasing it.
All right, cool. Thank you. Yeah, and I think this is something, if you guys recall back for our project one, when we did log transformation, not on time series data, but that was one of the things that we actually do is reduce that heteroscedasticity. In this case, we can kind of see it's a little different. But no, that's really great. And know that, again, this is like literally two like strategies on something that I'm sure like Aubrey can like talk a whole bunch about and saying all these different things you could do and what situations. So just know that there's so much more out there. Don't feel like it's like, oh, I know all this curriculum stuff. I'm completely done with this stuff. There's always more to learn, right? And that's hopefully a good thing, not an intimidating thing. Cool, thank you, Aubrey. So one other thing we can do to help kind of detrend, you know, basically get rid of that our trends in there, we can subtract out the rolling mean. So we saw from before the rolling mean is basically seeing how kind of averaging over previous points. So if we do this again, we can actually, let's see if we check this out. So you can see here, this is a rolling mean of about window of 4. So what we can do is actually subtract that part off. And we can see when we do this part, we can, oh, also know I'm getting rid of this these null numbers, because right here, as you guys can probably tell, I didn't subtract anything off here. So that's because the rolling mean didn't exist yet, because we're only looking at 4. If you had, depending on your data set, that might make sense to extend it further, or maybe just ignore those points because it's not going to be a drastic difference in your data set. Just know that that's why we're replacing this. And if I plot this out now, you can see here is that after I subtract this, like essentially that average out, you can start seeing like, okay, like we lose that like exponentiality. We can see a little bit of, there's still obviously, I like to say like the little bit of noise in there, is that we're still seeing this stuff in here. And that's good. We want us to be able to say, okay, cool. Like this is a little bit easier for us to essentially average over it. And this hopefully makes sense of why you would subtract off the rolling mean. You want to, if you start off, like for example, let's say for stocks, is if you start off at a high, you know, a high point in the beginning of the week, you're more likely to be at a higher point at the end of the week. Okay, it might still drop, it might still kind of raise up, but it's more likely that you're around that spot versus going from the very bottom to the very top. And this is where hopefully that makes sense of like actually subtracting that rolling mean. And depending, you know, this is in a lot of ways what we're doing is a little more art than it's like science of saying like, well, how big is your window? That window can be determined, you know, maybe dependent on the use case or your specific data set, or, you know, what domain you're actually looking at. Okay, cool. So thanks, Pretty. Any questions on that? All right. So one aspect of rolling mean that the curriculum also mentions about is the weighted rolling average. So just know that the weighted average, in this case, we're basically treating every single data point equally. But you can imagine, like, for example, if let's say I took a very large window of like 20, it's like, well, like 20 days for the stock market. The stock market price from yesterday is probably going to determine more about the stock price today than it was like 20 days ago. So what you can do is essentially say, well, things that were closer in time should be weighted more. And this is where you can actually give different weight and have a weighted average essentially. And you can subtract that part off. So there's some more documentation for this data frame, EWM. To be perfectly honest, I'm not 100% familiar with this part, but you can do these kind of things if that makes more sense for your specific data set, or honestly, if it just makes your more stationary time series. Cool. All right. And so this leads us to differencing. So basically, let's see here, run this up. When we actually, why do I have this linked over here? Oh, or .diff, okay. So we're subtracting off our previous, sorry, I saw a little thing. You might see that. It's called autocorrelation other sources. Yeah, and we actually, in the curriculum, is autocorrelation is mentioned too. So there's a whole big discussion on there in a good lab. Go forward. Just to kind of pull that out. Thank you, Aubrey. So for our differencing right here, basically, we are considering points that we're essentially seeing that difference between different points. And so here's an example for our New York Stock Exchange. So right here, we are differencing by a period of 1 day over here. And our original one, if I have this right, let's see, just gonna show you. You can see here, it's like this is the actual trend right here, or this is the whole time series itself. But by doing a difference of like 1 period, we can actually start getting rid of that, basically considering that lagging that extra point behind. This makes sense depending on like what data set you're looking at. So for example, this temperature over a decade. Well, in this case, you know, your period, you will expect the temperature to change, you know, over time. But like, for example, let's say, you know, the planet's warming up, you would expect to see like, okay, over multiple years, you would see the temperature increase and increase, but you also would get a time series that will be fluctuating throughout the year, since it's, you know, hot in the summer, cold in the winter, right? So you can basically do this differencing to allow you to kind of like, well, I'm going to difference it from 365 days, so basically a whole year. So you can see here is that I actually get a little better, this is the original rate here of the data. And you can see, like, even though it fluctuates throughout, you can kind of see there's this definite like pattern of the period, and you can see that's happening per year to year. And so it's like, oh, I know how, you know, basically, you know, the domain knowledge of like the Earth. It's like, well, the Earth tends to repeat these seasons every 365 days. You can subtract that part off, and you can now see that we got rid of that periodicity. And this could be useful, for example, like Aubrey had mentioned, like for like sales in certain quarters and stuff like that. If you know there's a certain pattern within that, that might make sense to change the period to make sure that you consider, you know, basically that fluctuation that goes through. Okay, cool. Sound good so far?
So guys, why would we want to know how different one point is from the point previous to it? Like, what does this bring to us, and how does it benefit? I've got all day. So let's look specifically at that stock example. Like, why would I want to know how different January 31st is from January 30th?
So you can see how frequently the stock is changing, and if it's like classified as a more like steady state price or something that's more volatile or from day to day.
Right, absolutely. So that could, when you're looking at stocks to invest in and you see that one changes drastically from one day to the next, if you're not a day trader, that might not be the right stock for you. And it might be labeled as steady growth versus high risk versus any other number of things that they call them. It could even change its Morningstar rating. Yeah, it's super important.
Thank you, Aubrey. Yeah. So hopefully guys can kind of think of like how you can apply this like time series. And I think, you know, maybe some of you guys might be more familiar with this kind of like concept. Maybe other times, like maybe it's just all completely new. Hopefully you guys are finding this actually really fascinating. I think it's pretty cool. Again, my personal expertise knowledge in this is not great, but this is why we have Aubrey too.